Good morning. Today I am M. Yovita from CSMC. Today I'll be presenting pipes, signals and basic threading from operating systems and system programming. Operating system allows multiple programs to run, communicate and share systems resources simultaneously. To achieve this, OS uses three important mechanics. They are pipes for process communication, signals for handling system level notifications, threads for parallel execution within a program. These three features form the foundation of multitasking and coordination in any modern OS such as Linux, Mac OS or Windows. For example, first we know about process. What is a process? A process is a program in execution. Each process has its own address space, memory, CPU registers, open files and systems resources. Processes are independent, so one process cannot directly access another's memory. Managing process consumes significant systems resources, hence it's called heavyweight. To make them interact, the OS provides inter-process communication (IPC) mechanics like pipes, message queues, shared memory, etc. Example: when you run two programs, a text editor and a web browser, they run as separate processes. They cannot directly share data unless IPC is used. Pipes. A pipe is one of the simplest form of inter-process communication. It acts as a unidirectional channel that allows data to flow from one process to another. Key concepts: write end, used by the sender process to write data. Read end, used by the receiver process to read data. Data written to the pipe is temporarily stored in a kernel buffer until it's read. How it works? The first process writes data into the pipe. The kernel buffers the data. The second process reads the data from the other end. Think a pipe like a one-way water hose. Data flows only in one direction. There are two types of pipes. Anonymous pipe exists only while both processes are running, used for communication between related processes. Example: a parent and its child. Automatically destroyed after use, common in Linux command pipelines. For example, ls-l grep.c. Here ls and grep communicate using an anonymous pipe named pipes. Exist in special files in the file system, used for communication between unrelated processes. Remain available even after the creating process terminates. Anonymous pipes are temporary. Named pipes are permanent until we delete it. Signals. A signal is a software interrupt sent to a process to inform it that an event has occurred. Signals are a form of asynchronous communication. They can interrupt a running process anytime. Why signals are more important? Allows the OS or user to control process, handle unexpected events such as errors, termination, requests, or child process completions. Signal meaning means interrupt generated by pressing Ctrl plus C to a program. SIGFPE is an arithmetic error divided by 0. SIGKI signal force terminate cannot be caught or ignored. Sick child ended sent to parent when a child process terminates. For example, when you press Ctrl plus C in a terminal, the OS sends SIGINT to stop the running program. Signal handling. When a process receives a signal, it can handle it in three ways. perform the default action. The OS take a predefined action, example terminate. Second one is ignore the signal except for unattachable uncatchables open ones like signal and sig stop. Catch the signal executes a user-defined function called a signal held handler. Now, basic threading. A thread is a lightweighted process that runs within a parent process and shares its resources like memory and files. Threads are faster to create and manage than processes. They allow multiple tasks to execute concurrently within one program known as multithreading. If a process is a house, threads are the people living inside, sharing the same rooms but performing different tasks. Basic threads. Improved responsiveness. UI remains active while background operations run. For example, file downloads. Resource sharing. Threads share memory easily, avoiding complex inter-process communication. Parallelism can take full advantage of multi-core processes with different threads executing on different cores simultaneously. Efficient resource use, lower overhead than creating multiple processes. The real world examples are a web browser has multiple threads, one for rendering pages, one for user input, one for background network requests. Thread management and synchronization. When multiple threads access shared data, synchronization ensures data consistency. Common mechanisms. Mutex, mutual exclusion. Only one thread can access a critical section at a time. Semaphore controls access to shared resources among multiple threads. Common issues. Race conditions. Output depends on unpredictable timing between threads. Deadlocks. Two or more threads wait indefinitely for resource held by each other. For example, two threads withdrawing money simultaneously without logging incorrect account balance. In conclusion, pipes connect processes for data transfers, signals allows communication and control between the OS and the processes. Threads improve speed and responsiveness through parallel execution. These three mechanisms together make modern operating system powerful, responsive, and capable of true multitasking. Thank you.